it's left or right, or maybe they're both. Let's just say left and right today. So then you could just table the distribution. And then you just put these probabilities down. You can just shortcut that of C and you say P1, P2, Pk. And the P's have to be fractions, they have to be probabilities, right? And then if you add them all up, you have to. Okay. So the F face on a die, if you assume the die is fair, that's a hypothesis in this class, right? The hypothesis is the die is fair. You might want to test that hypothesis, especially if you're playing a game of craps or high stakes. So an example, assume the die is fair. And then one side should be equally likely, right? So this should be. Okay. And then this would be my picture, right? I could just add. That would be the picture of the distribution. Now, it doesn't have to be fair. There could be many other distributions. For instance, on the second roll, maybe you're playing against a house. So you roll and get a 3 or something. And you have to make that point, right? Before you make a 7. You make a 7 on the roll, and before you make your point, then you crap out, and you lose to the house. So after your first roll, person running the game says, I think you need another beer. He looks at your cast beer, he pulls out his own dice, and then he wants you to roll a 7, so so for a second example, maybe 3 and 4 are more likely. Oh yeah, you just have a 7. In fact, this is what he wants now. So there's your second set of dice that you have this distribution. Okay? And you could have many others. How about a die loaded to high numbers? It's hard to think of a loaded die, but such things exist. Like it's probably a real art. But here's a die loaded to the high numbers. You might think of a spinner if you have trouble conceiving this. So there's plenty of distributions, right? For this simple experiment, there's actually an uncountable number of them, all right? So it's, probability isn't it? You always have to have an assumption if you put down the probability, and again in this class that'll be hypotheses, right? These would be alternative hypotheses. In the hand of a human, these are not numbers, so the bar chart would be like this. Let's do adult males. I think it's about 11% lefties, so the picture would look like this. 10% lefties. So that would be the picture of the distribution. read an article once where it said that it's only in humans that we have this disparity. Most animals are 50-50, so just after I read that, I tried to test my dog to see if he was left or right. Couldn't figure it out. Any questions on that? Now, if they really are numbers, we could talk about the mean and standard deviation. For one thing, everyone can do it in this class, all right, for these simple distributions. And it really helps when you have a concept if you can do a simple example. Right? That's a great way to study for classes like this, right? You read your concept and then you try to do an example that maybe goes with it, an example that goes against it. I mean, when you can start writing examples like that, you have a good idea of what the concept is. So the concept I want is the mean, right? And at least the mean and the variance. But here, you can't use categories like this. Doesn't make sense. So it's the range items. And again, you might say, well, define numbers. You could say left is 0 and right is 1. It's also called the expected value of x, so it's E of x. And this is the mean mu, right? Greek letter mu. This is the mean. And you just cross multiply the range and the probabilities. So what is the mean? What does the mean mean? It's the center of gravity, right? It's the center of gravity of your picture on the horizontal axis. So. The distribution is something like this. And the mean is probably others. In a simple example, class pairs. And, the mean would just be here's the distribution, okay? Now, since we know it's the center of gravity, you can tell me the answer, right? If it's symmetric, it's got to be. So this better come out to be the middle, which is what, 3.5. So just the verification, you just do this, right? 1 times 1 6 plus 2 times a 6, and so forth and so on. Right? So then you just have to add the first 6 positive integers. It's what? 21. 21 over 6. Well, big surprise on that, right? That's what it's got to come out to be. And I don't know how many of these things we'll be doing in this class, not really very many, but if you're doing one and you recognize symmetry, you can just write down the input. Symmetry is always worth recognition. And that's true for this one too, even, oops, not this one. do that one in a second. It's certainly true for this one, right? It's still symmetric. So the mean here has got to be 3.5. So if we switch dice on you and you're computing the mean as it goes along, it's going to be 3.5. You're not going to get a different answer. This one it won't be, right? This one's going to be, it tells that all the mass is way up here. That's going to move the mean to the right. Okay. And this one, you cross multiply and add. It's actually the sum of the integers squared. So, it's going to be 13 thirds, right? 2 1/3. Right? If you don't know this number, you can do it. You can just do it. Well, that's good exercise. Okay. Well, you can see one trouble with the mean already. You can really change things. So this is 1 through 5, right? You want to screw this way on to 200. And there goes the mean, right? The mean's going to chase after this guy. How balanced you get. So we asked that. So these would all be 1/5, right? So you could compute the mean here. It would be the sum of the first 5 positive integers, right? And then you have to add this to them. So that would be what? 215 over 5. Oh, wait, this got to go over 6, right? Be about 36, right? 35 and 5 6. What's that? 25. About 36. So in statistics, we'd say that the mean is not a robust parameter. Okay. It's very sensitive to outliers. Okay. It's very sensitive to the tells of the distribution. Okay. Now the mean is a location. I should have backed up here. Well, I'll define it that way. Define it that way now. Mean is a location parameter. It's like a measure of center of the distribution. All right? Mean is a location parameter. Measure at the center. Center. And then we can add to that now, we can say the mean is not a robust location. I don't know what the center is in this picture, but it's certainly not 36. 5/6 of the time you're right here. It's only 1/6 of the time you're out here. And I could even change the picture more drastically, right? I could have 1 minus epsilon of the time you're here, and epsilon of the time you're out here. And if I push that out far enough, the mean will still run to infinity. Okay. The mean chases the tail. So it's not very good. It's not a very good measure. Okay. And then how about another parameter? I mean, again, these these two distributions have the same mean, but they're not the same. So you certainly need another parameter, right? At least another one. Well, how many parameters do you need? If you're in stat, you should be able to answer that. You need an infinite number. So you're not going to get a function with several parameters. This measures of location and measures of dispersion. Variance, spread, etc. Okay. There are other measures of location. We'll talk about them. For the discrete case, like the median doesn't make sense most of the time. I just rather wait till we get to continuous. Again, the idea of introducing the mean now is it gives you something you can calculate. So maybe you get an idea of what the mean means. And, that's true with the second one too. I mean, the only one we'll look at the moment is the variance. The variance is how the distribution varies about the mean. So already you know it's not going to be robust. It's just this expected value of variable minus. And then we can do this in the discrete case. It's just going to be this. This looks great until you're looking at a distribution and the mean turns out to be 4.32478010. We don't want to do that. So there's a shortcut formula. You can rewrite this as this. So if you're going to do them by hand, you usually want to use this. Okay? Not just the expected value of that squared. And we could go back to our examples, although I might use the computer for the second one. What's the variance for the die? Subtraction. I'm going to get a fraction, and I have to square it. Instead, we'll just use the second formula. We have to square the range values, and then just cross multiply those with the probabilities, and then add them up. So we can go back to our distribution here. And we just have to square these, and then do the multiplication. Okay. Actually, we've done it. Okay. But again, it's like the technique, it's not the answer. But this is what it would be. That's what you would have to do, right? See, I'm squaring and cross multiplying. Then you have to compute this, and again, you can. It's a sum of the first 6 positive integers squared, and there's a formula for that, but you can just add them up, right? So 1596. Is that right? It's 6. 0.16. So then the variance would be someone should check. Yeah, I'll use my computer like a calculator. Yes. It's 2.92. So this comes out at 2. Now the variance measures the spread of a distribution about the mean. So just from that description, tell me which one has the most variance. Because these have exactly the same mean. In both cases, the mean's 3.5. This variance turned out to be 2.92. So this variance is going to be what? Bigger or smaller? Smaller, right? Because the mass is more packed in closer to the mean. So the variance is measuring the spread. In fact, go back to that one picture we had with the disaster. Okay, 200. And when you calculate that one, when you do the expected value of x squared, this will be 200 squared times the 6. So that's going to just kill it. Variance is easier to build up. We can do this one. checking out, I just do it by the computer. So I need what? I need the second nominal, so it's but that is expected value of x squared will be minus 16 over 8. So that's 13.5. So it would be 14.5 minus 3.5 squared. Okay? So it would be 2.15. Here you can see what it is. I just did it. Oh, I was going to write it for it, but so it comes out to 2.15, and the other one's 2.9. Any question on the variance? Again, it's not robust, but it's just an illusion. But it's very useful. Any questions on the mean of the variance then? Okay, so you're set on those?
I think the typo in the computer.
What did I do? What did you do?
2.25. I thought 14.4.
2.25? It's still small.
Yeah. I know.
Good, okay, thanks. You've
I
got to
make-
check
I
my
make
arithmetic.
that mistake.
I've made some horrible errors in checkbook over the years. Thanks. I have to keep them honest. I just continue bullshitting. So. Anyways, okay, so let's do some examples of name ones. Again, it's the simplest of all models we talk about, but it's one of the most useful. Okay, it's the Bernoulli, and we'll make it numbers today, so it's 1 or 0 if it's success, right? So you have a trial that ends either in success or failure. And we'll just write 1 if it's a success and 0 if it's a failure. Okay. So P is the probability of success. And the distribution of X is this. Now if we use Q here, Q is 1 minus P of it. It's not something new. Definitely P plus Q is equal to 1. Okay. The hand experiment we just talked about would be this, right? So for an adult male, let's say the probability of lefty is is 10%, then P would be 0.90 if success is right-handed, right? And it would be, Q would be 0.1. Right. So the example is the example. That would be a probability model. We certainly have enough data on that to count these numbers. Okay? And then what's the mean? You can actually compute the mean of this, right? It's 0 times Q plus 1 times P for P, which makes sense. Okay, so the mean for the hand is 0.9, right? If I do the experiment, I expect x to be 0.9. Well, you know it's either 0 or 1. That would be what the mean is. Okay, now to do a chart like this, this is 0, and I put these together because these numbers have the right meaning. So this mu is at 0.9. Okay? It's even steeper than this, right? It's tall. And then you could compute the variance, certainly just due to the second moment, right? So it'd be 0 squared times Q plus 1 squared times P of P. So the variance would be expected value of x squared, right, minus the mean squared. So it would be P times 1 minus 1. Doesn't have much meaning in this picture, right? Okay. Now, this experiment, we can also look at the sampling distribution. In this case, this is the model, okay, not the binomial, the Bernoulli. Usually, it's not always true. We've got a good example where that's not true, but the sampling distribution is, and we can talk a little bit about sampling because for the binomial, you just repeat this trial independent times, and you don't change any conditions. And that's the definition of random sample. So you can get an idea of the random sample in this very simple context. So the second example is binomial in P, and you just repeat the Bernoulli experiment. N times. And for n trials. And then the trials are independent of one another. And two, we do not change conditions. Conditions remain the same. Okay. And again, a very good example of that is the presidential rating. We're going to do the presidential rating, so we're going to, let's just put that in this context. So this would be the model, right? You either project the way Obama's running the government or you don't. This would be the probability that a person says yes, right? This would be yes or no. Going better than 50% in my mind. After this election, I realized that Obama was a very shrewd politician. he won the fiscal cliff. Too bad the Republicans don't realize. So I think that seems a better point of view. But that's the end of my politics. But anyways, this would be the model, right? And then a Gallup poll, you would randomly select these people. And there's a lot of effort put into this, okay? You've got to make sure it's representative. In fact, you might even break it up into sections. I don't think they do that anymore on these, so I'm not sure. Okay. So you have to do random calling, and the people doing the calling must ask the question in the same way. I remember once I was looking at a survey in the lab, and they said, oh, this survey was done by, they had like 100 responses. I said, well, that's not very many. And they said, well, it was done by 10 people. And then they explained what some of these people were doing. And I thought, well, you don't have a sample size 100 like I thought. You have 10 samples of size 10. So you know, these people that call, they have to say it the same way. I mean, if they're, they can't show any bias. So, so citizen people can vote. Two conditions of the. You've just got to have a short time frame. Or conditions. You could do it for a simple experiment too. Okay, but this would be the binomial. I'm going to repeat this 10 times. And then we just said the variable of interest, I'll call it x, or else x would be, well, for today we could call it y, would be the number of successes. But notice your trials are this, right? X of I is 1, your success on ith trial, 0 otherwise. Right? So this y is just, you just add up the x's. So if you're a statistician, what kicks in? Central limit here, right? You're adding up a bunch of things. Independent. So you will not be surprised that this distribution has a mound shape. Okay? Now, how about the distribution of y? It's not as easy, right? We'll write down a formula. We won't actually probably use it in this class. First of all, the range is from 0 to n, right? You could get all failures or all successes or anything in between. And then a few of these you can get, like the all failures means you failed on the first trial, and on the second trial, and on the third trial, etc. I'm using independence, but that would be the probability of those. And it's like an intersection, right? And they're independent trials, so it'll be the product of the probabilities. So each probability is Q for failure. So it's Q to the n. So there's a couple you can get without much thought. And the same thing with all successes. But then you run into snags. Suppose y is 1, then, well, this will be an easy one too, because you can fail on the first trial, or you can fail on the second trial, or the third trial. And each of those strings has probability q to the n minus 1 times p. So, I'm going to break this down. But that f is just drifting down to the last one. And these are independent again, so it's q n times. Likewise, you get this one, same way. What's the others? Well, then you have to do a little bit of combinatoric theory. It's not hard, but it's not. Well, it's not part of this class at all. Just give you the answer. Actually, it's nice to note that in this example, you can get an answer in closed form. This is n choose k, that dumb thing I wrote at the beginning. And it's just n factorial over n minus k factorial times k factorial. Remember, the k factorial is k times k minus 1, etc. And if you come across at 0 factorial, okay? It is kind of neat to get that in closed form. I often wonder what would have happened to science if a few things like this didn't turn out. For instance, the Wilcoxon statistic, as you'll see, is a very simple statistic. Okay, you cannot get its distribution in closed form. So, what if the king had assigned the problem to the Bernoulli brothers? In his gambling game, the thing he was interested in was the sum of the ranks, like the Wilcoxon. The Bernoulli brothers couldn't come back with a nice answer. But here we get this in closed form. And actually, it did more than that because it was in closed form. They ended up with a proof of the central limit theorem for the binomial case. Okay. So how do we compute that in this class? Well, you go to your package, right? I'll do it in R here, but when I build Minitab on my old laptop, which I hate to do, we can do it with Minitab. You can do it with your favorite package, right? Again, if you have like a favorite package you want to use for this, just investigate it. How do I get a binomial probability? Maybe it's very important for you to compute the following probability. It's Obama's rating, and it's supposed to be 56%, but in my poll of size 200, only 43% chose Obama. I mean, gave him a favorable rating. See, I wrote it down. who was shaken up on this because he should at least get over 100, but you only observed 88. So certainly the probability you want to compute is, and then you think, do I want to really know the probability of 88? Well, that's sort of absurd, okay? Think of even a bigger experiment where you have 1,000 trials, and the probability of success is a half. Okay, what's the probability of getting 500 successes? It's very small. And you can make it go to 0 if you just let n go to infinity. So that's not the thing of interest. I think the thing you're really looking for is the probability of 88 or less. I think this is the exam of interest. Okay. Is that hard to get less than or equal to 88? So now you're ready to compute this. You know the formula, so here you go. It's a sum from j equals 0 to 88. 200 choose j. 0.55 to the j. 0.45 to the 200 minus j. So now you're really, right? So even your side rule is not going to help you. But the computer does, right? Doesn't matter. Doesn't matter if it's 200 or 10 billion. Now, I'll give you the answer in R. It would be P by 9, 88, 200, 0.55. Actually, on a test, we could invent notation for this. I don't know if we need it or not. I can't. So, and again, some of you might even have this on the calculator. So here's the answer. Yeah, it's 1 out of 1,000. So then, this is class in statistics. What would you say?
Rather unlikely.
Yeah, it's rather unlikely, and then you might, what? You might question the experiment, make sure it was done right. If that's true, then you might question the rating, right? That would be your hypothesis. See, this is what? This is actually a p-value, right? It's an observed significance level, and I'm testing the hypotheses that p is a 0.55 with this observed significance level. It would be a one-sided. You might say, well, it should be two-sided. We don't know anything. We would just double that probability. I mean, I'm getting ahead of myself here, but in this class, that's the kind of probabilities that I can think about. Okay, so that's the street one. Why is this? Poisson experiments like this, okay? You're observing a process over time and you're counting the number of events. It might be like the number of calls coming into a switchboard, the number of people entering the store, the number of customers, The number of failures or something. Like a big new Boeing jet, okay, it's been 2 failures. I guess they haven't been horrible things. But, so you're counting the number of breakdowns, et cetera. Okay? And we're always doing this, right? We're always counting things like that over time. And the Poisson process is worth talking about because most likely what you're counting is a Poisson process. So you're counting events over time. There's 2 axioms. There's 2 axioms. In a short time interval, you can only see one event happen or no events. In the probability 1 event, let's say the time interval is length delta t. So you're counting events over time, and in the short time, probability 1 event is proportional to the length of that event. The lambda squared. It's a probability because you can make delta t as small as you want, no matter how big lambda is. So it makes sense. So in this short time interval, I can either see none or 1. So it's like 2 buyers cannot come into the store at the same time. So this rules out with what? Black Friday, right? I never wanted to go shopping on Friday, Black Friday, right after Thanksgiving. They even showed it wasn't an ad, it must have been on the news. I don't think any store would show this. Or what happened like last year, there was one store, well, this year, the workers got trying to do one store, right?
There was a fight.
Yeah. So I got them glad my wife stays on and does her shopping on the web. So I can have to pick the bills. Anyways, you have to go out things like that. And then the second one is disjoint intervals. Well, disjoint time. Or independent. That's not good. So if I have intervals like this, or disjoint, what happens in this interval does not affect what happens in this interval. So the events are independent. This is the one that often breaks down. Independence is a very crucial assumption in what we do, and often it's just the one that's a little bit shaky, all right? It's hard to imagine in a normal day 2 customers coming in the door at exactly the same time, okay? Because I can make delta t as small as I want. But, okay, someone's coming by the store, say you're in a mall where you have several stores about the same, and they're coming by the store and they see, God, there's 100 people in that store at the moment. Then they just walk on down the aisle to the next store. Then, you know, what happened in And this interval has affected what happened in this. So that's one that's a bit shaky. You've probably done that. Well, now we have these ATMs. But suppose you have to go to the bank and the ATM area is crowded, you might just go to the next branch. Well, this would be the Poisson process, and this would be the Poisson random variable. And you can get its distribution close to the first one. It's not as bad to compute as the binomial. And many years ago, that was important because often this is really like a binomial. See, if you take delta t to be 1 over n, this is like success because it's the probability of success would be a 5 over n. So there's a binomial, you can use a Poisson to approximate the binomial. That's not important in this class, so I don't go into it anymore than that. If you take a course in probability, we'll go through that class. So when you use a slide rule, you really get used to approximating numbers quickly, because when you use a slide rule, the decimal point gets lost. It's on the log scale. So you have to know where to put the decimal point when you're done with your messy calculation. I think that part's lost. Oh, okay, I forgot, for the binomial, the mean is n times p. It's n times, if you flip a fair coin 10 times, you expect 5 heads. Oh, and I meant to say something about the distributions. The way you finish this, the variance is NP stick with the points. The Poisson, lambda, we have lambda, this becomes the average number of events. Lambda is the average count. Interval. One unit of time. It's a number. It's the expected number of events that occur in 1 unit of time. Okay? Say that backwards. It's really good. Another good example of a Poisson is like a number of tornadoes that come down and that hit, say Kalamazoo County in a tornado season. Okay, lambda would be the expected number. I don't know what it is, 4 or 5 or whatever. Maybe it's probably too many. And so the expected value, if you're counting over the interval of length, time of length t would be lambda times t. And the variance is the same. Okay. I meant to say something about the shapes of the distributions. For the binomial, we had that formula, and what's the shape of the distribution? You can do it in one sentence. Okay, again, the range is 0 to n, right? So the probabilities increase until the mean, and then they decrease. So it is non-shaped. So, you know, if you draw a picture, say n is 100 and p is 0.1, then you have mass from 0 to 100, but it peaks at 10. This will be the peak of the distribution. So those bar charts, I'll just draw a smooth curve, look something like this. So if p is less than 1, I mean less than a half, then it's going to be skewed right. If p is greater than a half, it's going to be skewed left. And if p is equal to 1/2, it will be symmetric. Okay. So again, I need to emphasize this with the Poisson. If n is 100, if p is 0.9, then it's just the reverse, right? So it will be skewed left. Okay, and then the Poisson, how many events can you have in a unit of time or whatever? Let's say time is 1. You could have 9, you could have 1, you could have 2, and then it's uncountable. The probabilities, of course, will decrease, but it will peak. The distribution peaks. T equal to 1 means lambda. Distribution peaks. So lambda's out here somewhere. Okay, that's where it peaks and then it goes down. So it always has a long tail below. Poisson will come up a few times in this class. Okay. It's like the number of kids in a family. Probably approximately Poisson. Many of the counting distributions are approximately. Many of the counting processes are Poisson of interest. Or approximately Poisson. You can see why, because those assumptions are not that hard to satisfy. So when we talk about continuous, we ought to come back and touch on doing a lot of things. Because you live in a Poisson world, in that sense. And many people don't realize that. They think they live in a uniform. So I want to come back and talk about that, but I'll wait till we talk about continuous distributions of the graph. Okay? I think that's really all I wanted to say about discrete.